Hello AP Physics students, this is Dr. Berenzi and this is lesson 9.1.3. And our objective for this lesson is that we're going to be able to explain why it doesn't hurt to put your hand in a hot oven until you touch the metal. So let's figure out the mystery. In order to explain why physicists, or how physicists would explain that, I have to introduce to you the phenomenon of heat. You may think of heat as something that makes you feel warm, and in a sense that's true, but let's give it a more physical definition. The heat, heat is a bulk transfer of molecular energy from one body to another. What do I mean by that? It's like molecules. Of course, we learned that temperature is like a way of characterizing the average amount of kinetic energy in molecules in a particular body. And when two items, actually, they don't need to be in contact, as we're going to find out, but let's say when they do come into contact, we have some of that energy transferred from one body to the other. Now, in order for heat to be transferred, two items have to be at different temperatures. So on the left-hand side here, we have two people who are shaking hands, and let's assume that both of them have a body temperature on their hands of 39 degrees Celsius. Okay, we know it's 98.6 Fahrenheit, but that corresponds roughly to 39 degrees Celsius. Now, what would happen in this situation on the left is that this person's hand on the left, they have an average amount of kinetic energy in in the molecules in their hand, and those are going to bump into the molecules on this other person's hand, and on average, these bodies have the same amount of energy on average. So, you could say to some degree or another, some molecules are transferring energy from the brown hand to the white hand, but there's also the same amount of transfer from the white hand to the brown hand. And so there is no net transfer of energy. So we would say in this case, when temperatures are equal, there is no heat transferred. The only time where you get heat being transferred from one body to another is when there is a difference in temperature. So let's take this poor unfortunate soul on the right who has chosen to make a foolish decision. And we know that this person's tongue is at a temperature of 39 degrees Celsius. The metal flagpole is definitely at a temperature below 0 degrees Celsius. So let's say maybe minus 10 degrees Celsius. That would be a rather cold day. And when this person's tongue comes into contact with the metal flagpole, this person's tongue on average has a lot more energy in the molecules, so there is much more heat being transferred, or energy being transferred from the tongue to the flagpole than there is going the other way. So on average, we would say that there is heat being transferred. This person's tongue is losing energy, and the flagpole is gaining energy from this transfer of molecular energy. So in this case, heat is transferred, and it's always transferred from the warmer body to a colder body. Okay? Because on average, it's the hotter body that ends up losing or transferring more energy than the colder body. Alright, Now, there are three primary ways in which heat is transferred between two bodies, and the first one is called conduction. Now, conduction takes place when two bodies are in physical contact with one another, and when that happens, molecules from the warmer body, on average, transfer energy to the cooler body. Now, what I mean by on average, just in case I wasn't clear in the previous slide, is we know that there's like a distribution of kinetic energy. I showed you this in the demonstration. So if we plotted a little histogram right here, there would be a lot more molecules with a higher amount of kinetic energy than over here with the cold body. If we plotted that histogram, we would get a histogram like this, where there is fewer particles that have high kinetic energy. Now there are a few up here, and if they were to collide with some of these particles over here, there would be a little bit of transfer of energy from here over to here, but there's a lot more transfer of energy from this direction over to that one. And so we would say that the hot body is transferring heat to the cold body. So there is a formula to actually calculate how much heat is transferred. Now, heat is a transfer of energy. We usually designate heat by the letter Q. Okay. And that is in joules because heat is a transfer of energy. This T is an amount of time. So this formula is actually talking about the rate of heat transfer. There is this letter kappa. It is a Greek letter. So kappa is what is called the thermal conductivity. I want to say constant. Hold on here a second. Oh, thermal conductivity. Okay. It's just called thermal conductivity. It's been a while since I've dealt with this topic. Thermal conductivity. And that is something that you would have to look up in a table because different materials have different thermal conductivity. And then the area of contact between the two materials is A. And then the D is the thickness of the barrier. Okay, so you could imagine that if this were actually drawn in two dimensions, let me see if I can finagle a two-dimensional drawing real quick. I might be able to do it if I can hit the right spot with this line. There we go. Let's make this look two-dimensional. Right, roughly two-dimensional. All right. So this would be the area, the amount of area in contact between the two bodies, and then this down here, oops, let's try that again. This down here would be our thickness of our barrier D between the two materials. Okay, so that's what happens with conduction. Now, I'm already going to help us answer our objective question. That is, why is it that when you stick your hand in a hot oven, it doesn't feel uncomfortable? I mean, it feels warm, but not uncomfortable until you touch that metal bar, right, or the metal shelf in the oven. Well, this formula actually gives us the answer right here. It turns out, like I said, that there are this conductivity, this thermal conductivity, changes for different materials. The thermal conductivity of air is very low, which means there is a very low amount of energy transferred every second from the hot air into your hand. And so your fingers say, okay, this is warm, I'm warming up, but I'm feeling okay. Nothing tragic. But once you get into contact with the metal inside the oven, that metal is still at the same temperature that that hot air is, but the thermal conductivity of metal is very, very large, much larger than air. And so you are suddenly going to get much more energy transferred into your hand per second, and your fingers start to say, "Youch! Get this away from me, NOW, ASAP." So that's why an oven doesn't feel uncomfortable until you actually touch the metal. Now, there are a couple other ways that heat is transferred between hot bodies to cold bodies, and the second way that heat can be transferred is called convection. So convection, this is when you have pockets of warm fluid, they get heated, they expand, and that expansion causes the density to decrease. And because the density decreases, now that little pocket of warm fluid has some buoyancy, and that buoyancy causes the warm air or the warm fluid to rise. And that warm fluid displaces some of the colder fluid that is farther away from the heat source. And that colder air, in turn, has to go somewhere, and so it ends up going down, and then it will end up getting heated up, and then that pocket in turn. So there is this, what we call a convection cycle going on. If you've ever watched water boil, just before it comes to a hard boil, and the water starts to become steam, you might actually notice that the water starts to move a little bit before it actually comes to a boil. Well, you are actually witnessing convection. Sometimes it's actually easier to see it in a pan of deep frying oil, because deep frying oil doesn't boil as, it doesn't come to a boil at the temperatures that we have on our stove. So you will actually be able to see better these little pockets of warm oil that move up, and then in turn the colder pockets of oil move down, and you might want to check it out sometime if you're not too busy getting ready to deep fry some chicken or something like that. Okay, so the third way that heat is transferred is by what's called radiation. Warm objects emit infrared radiation. Actually, all objects emit infrared radiation. And this infrared radiation causes the warm object to lose some energy. I mean, we are taking energy from that kinetic energy in the molecules, and some of that is lost to this radiation, and this radiation goes out, and that gets absorbed by a colder body. On the left over here, you actually have an infrared camera, and you'll notice that this person's hand is very red and very intense because this person's hand is at a higher temperature than anything else in the room. So this is actually the way that night vision works. Is actually it's basically an infrared camera. It's a thermal imaging camera. It is looking for this infrared radiation that is emitted by by objects, and the warmer the object is, the more infrared radiation it will emit. And what will happen is that this infrared radiation will actually be emitted and be absorbed by other objects. Maybe colder objects, like, say, all this stuff that is purple here. It'll get a little bit warmer, the guy's hand will get a little bit colder, and by the way, that's why we got to keep eating in order to keep our body temperature at 98.6 Fahrenheit, is because we are constantly losing energy through the things we do, and we're actually losing energy through this radiation. Now, you could actually calculate the amount of energy that a body loses every second, and that's given by this constant P. This is power. Oops, power. And power is energy per second. Okay. So it is, in a sense, the rate at which energy is lost. Per second. Okay. And that is given equal to a constant, which is the Greek letter sigma. Not sure if you have ever been introduced to that Greek letter, but there it is, sigma. Times the area of the object. And then we have a difference, but it's the difference in temperature raised to the fourth power. So this temperature is the temperature of the body. Okay, so in this case, it's the person's hand, so the body temperature. Okay, and this has to be in Kelvin, just like all the other laws that we've been dealing with so far. And this is actually the temperature of the surroundings. So T sub S means surroundings. Surrounding. Ugh, that didn't turn out too well. Let me try that again. Let me put the arrow in a different spot. There we go. Surrounding. And so because we have, our bodies have a higher temperature than room temperature, that means that there's some energy being transferred every second from our body into the surrounding air. Alright, so those are the ways that heat is transferred. Talk to you a little bit about what heat is. And I've also shown you, or defined for you why it's okay to stick your hand in a hot oven. It's 300 degrees Fahrenheit until you actually touch the metal. We'll get a chance to work with these equations a little bit more tomorrow, and I look forward to seeing you then. Bye.